Good morning, dear students. Let's revise what we have studied yesterday. Yesterday, we have studied about the internal energy. We have seen that internal energy can be changed by doing some work, or it can be changed by doing or by applying or providing heat or removing the heat from the system. So we have derived an equation that tells us that delta U is equal to Q plus W, where Q is known as the heat exchange, whereas W is the work done. And then on the basis of that, we want to solve some problems. So uh, let's move to the problem. We have this problem: express the change in internal energy.
You have to remove all this horrible. No papers
Internal
and all you
energy
should
of a
respect.
system when no heat is absorbed by the system from the surrounding, but work W is done on the system. What type of wall does the system have? That's what we need to understand. So let's try to understand it. Uh, do you understand the question, my dear students, or should I read it once again for you? Express the change in the internal energy of the system when no heat is absorbed by the system from the surrounding, but work done W is done on the system. What type of wall does the system have? So here we need to find out the type of wall that the system has, and here we are provided the information about the change into the internal energy. So this is how we truly study about the internal energy here. Let's look at the situation and understand it. Here you can see that no heat is absorbed. When no heat is absorbed, my dear students, we can say that the heat content remains the same, and when the heat content remains the same, we can say it is the adiabatic process. But work is done. So as the work has been done, my dear students, we can understand that the type of system that has been changed is very different. And on the basis of that, we can say that the work done is equal to change in internal energy is equal to the work done W, and the ball is adiabatic because the work is done into the adiabatic manner, and ultimately we lead to the answer. That is what it is known as the adiabatic process. Now, my dear students, we need to move to the next question. No work is done on the system, but Q amount of heat is taken. So there is no work which is done on the system, but the Q amount of heat is taken from the surrounding and given to the surrounding. What type of wall does the system have? See, here we need to study that no work is done on the system, but Q amount of heat is taken out from the surrounding. So we can write that as there is no work done, we can say that delta U is equal to uh, Q plus W. That's what we can write. So here we can write Q plus W, Q plus W, but the work done W is equal to 0. So we should write delta U is equal to Q. But as according to the sign convention, heat is taken out. So as the heat is taken out from the convention, we should write minus Q. So here we have minus Q. Thermally, and as you can see that heat is taken out from the system, the wall for the system was the conducting walls. So ultimately, as delta U is equal to minus Q plus 0, work must not have done. So we can even think of isochoric wall. So here even we can think of isochoric wall because work done per P delta V, and if delta V is equal to 0, the situation would be same. But still, my dear students, we can surely say that the ball is thermally conducting because the heat is taken out from the system, and this is how we understand this problem. Then the next situation, W amount of work is done. So here W is available by the system and Q amount of heat is supplied to the system. So we have supplied to the system Q amount of it. What type of system would it be? So what type of system? We have studied about the various types of systems. What are those various types of systems that we have studied, my dear students? We have studied about the open system, closed system, an isolated system. In open system, both the matter as well as the energy can be exchanged. In closed system, only the energy can be exchanged, matter cannot be exchanged. In an isolated system, nothing, neither energy nor mass can be exchanged. Here you can see that W amount of work is done and Q amount of heat is supplied. That means the energy has been supplied, the wall is not adiabatic, and this is how, my dear students, we can say that there is no exchange of matter, but there is an exchange of energy, and we can say that the system is closed system, and that is why delta U is equal to Q minus W. Now, why do we put minus W? You can easily see here that W amount of work is done by the system. So, as the work is done by the system, we can say that there is a W is equal to negative or work done is negative, my dear students. This is how we understand. Now, my dear students, we want to study the uh, applications of the first law of thermodynamics. So many chemical reactions involve the generation of gases capable of doing mechanical work or the generation of heat. Many chemical reaction involves the generation of gases which is capable of doing mechanical work or they are capable of generating heats. So here, my dear students, we can easily understand that it is important for us to quantify these changes and relate them to the changes in the internal energy. Here, it is necessary to quantify these changes and it is necessary to relate these changes with the internal energy. So, let us try to do it. But before we move on, let us first understand the various types of work, my dear students. We can have pressure volume work, that is W is equal to P delta V. We can do some mechanical work that we applied the force and displacement takes place. We can do the work done by gravity, that is mgh. Suppose a substance is for here, and if you move it to here, it the height of the substance has been risen to the h, and thus as the height has been improved, you can easily improve it, or you can have this height h. So work done to the gravity, W is equal to mgh, and this is how the work done, W is equal to mgh, where g is equal to the uh, acceleration due to gravity, height is the change into the height, and m is the mass of the substance. And there may be many other examples, my dear students, that we can understand. For example, if we do the electrical work W is equal to minus NFE. Here, my dear students, we are already aware that Q is equal to NF. So as you have Q is equal to NF, these represent the charges, and E is equal to the EMF or electromotive forces. Here F is known as the Faraday constant. So which is equal to 96500 or 96482 Coulomb. This is how we understand, my dear students. Now, so these are the various types of works that we can do. First of all, let us understand, or let us concentrate on the nature of the work of a system, or nature of the work for a system can do. we will consider only mechanical work, that is the pressure volume work. So we just consider the mechanical work, and this mechanical work is here we choose the mechanical work that is done by the applying pressure and movement of the piston. So let us consider a cylinder which contains 1 mole of an ideal gas fitted with a fractionless piston. Please remember, my dear students, that here we generally choose the frictionless piston. Even we can have the weightless piston also. So we can choose the frictionless and weightless piston. The volume of the gas is VI, that is the volume initial, and the pressure of the gas inside is P. So here, my dear students, the VI is the total pressure of the gas initially. So VI represents the total pressure of the gas initially inside the cylinder, and P represents the pressure of the gas inside. So this is how, my dear students, we represent the pressure and volume. Now let's look at the figure that we have seen here, and we'll understand it well. You can see here, my dear students, that initially we had this piston, this cylinder. In this cylinder, the external pressure is PEX. We apply the external pressure. Due to the external pressure, the piston move inward. The piston move the length of L, and it reaches to the final situation. So initially the volume was this, which is shaded by the green area, and then finally the volume remains this. The initial volume we consider it as a V initial, and the final volume that we consider here is V final. The pressure initially which was applied to this initial pressure to final pressure PEX, and under the PEX pressure the change in the volume, that is delta V, takes place. This delta V is V final minus V initial. So here we can understand that we have V final minus V initial. So we can write V final minus V initial, and this delta V is the change into the volume that you can see here, that this change into the volume is brought about by increasing the pressure. So this is how, my dear students, we study. Here in the figure we have seen, or we have explained, the work done on an ideal gas in a cylinder when it is compressed by a constant external pressure. PEX in a single step is equal to the shaded area. So here you can understand, this is the area which is P external multiplied by delta. That is your, this is your P external, that is, you can consider it as a length, and this is your delta V. So for this area, we can easily write P external, because this area is length into the breadth, and that is why the length is P external, breadth is delta V, and that is why it is L into B, length into breadth. Length is P external, and breadth is delta V, and this is how we can write this shaded area is P external multiplied by delta V. If external pressure, now let's understand, if external pressure is PEX, which is greater than the internal pressure P, piston is moved inward till the pressure inside become equal to PEX. Let this change be achieved in a single step. Remember, here we are going to use the single step, and the final volume be VF. So we will have the final volume, that is VF. During this compression, my dear students, suppose piston moves a distance of L and its cross-section area is A. So when volume changes, my dear students, it is a cylindrical volume. For cylinder, my dear students, we can write pi r square h. This is the volume of the cylinder. Here pi r square is the cross section area, and this is the length or the height up to which the cylinder is having. So here, if this is the h, Now we are aware that pi r square represents the area or the cross section area of the cylinder, which we write it as A, and h is equal to the height of the height, or here we consider it as a length. So volume change, the change in the volume, my dear students, we can understand as A into L. Now how A into L, you can easily see from this, that this pi r square is equal to A. We can relate this pi r square is A, and here height is equal to length, and that is why the change into the volume delta V is equal to A into L. For this change, we can even write V final minus V initial, because V final is greater than V initial. This V final minus V initial gives us the negative value. So this is how, my dear students, we can study the change in volume. So total volume change delta V is equal to V final minus V initial, which is also the multiplication of the A into L. Here pressure due to the which the volume changes, that is compression takes place, is equal to the extra PEX, which is the pressure. So we know that pressure is equal to force divided by area. Now here, my dear students, therefore force is equal to pressure multiplied by area. So now we can understand that force is equal to pressure multiplied by area. So in that sense, my dear students, work done is equal to force applied multiplied by distance moved. That is what it is, the simple definition of work. Suppose there is an object, if you apply some pressure to it, it moves to this distance. Then suppose this distance moved is L. Then and if you apply the F force, then the work W is equal to F into L. So the force applied, work done is equal to force applied into distance moved. Force is equal to pressure into area. So you can write force is equal to pressure into area, and distance moved is distance moved. So ultimately, we come to know from 1 and 2 equation, we can write W is equal to P external multiplied by delta V. But delta V is minus because V initial is greater than V final. So my dear students, V final minus V initial gives us the negative value. So this is how we get the negative value for delta V, and that is why we personally minus delta V, the minus sign we put it outside, and finally we write work done W is equal to minus P external into delta V, but instead of delta V we can write V final minus V initial, and that is why minus P external is equal to V final minus V initial. Here negative sign represents that the work is done on the system. Here the negative sign represents that the work is done on the system, and that is why P external is greater than P internal. Where P external is the external pressure and P is the pressure of the gas inside. In case of comparison, work is done on the system. So here if we put the value in equation, work done W is equal to minus PEX into V final minus V initial. Value of V final minus V initial should be negative, and thus in calculation we get the value of work done positive. So if we do some problems, we will find that the work done should get the final value which is positive. If we plot a graph of pressure versus volume for the above work done, we get the following graph. Now my dear students, here whatever the work done, if we plot a graph of pressure versus volume, we find such a graph. Here is the graph I am talking about, that if we plot a graph of pressure versus volume, my dear students, we get such a graph. Let us look at the graph. I am talking about this graph, my dear students. Please pay attention that if we have the graph of pressure versus volume, we get such a graph. In this graph, you can see that on y-axis we have pressure, that is P. On x-axis we have volume, and then we plot a graph. So as we plot the initial volume was this. Then you see what happens when the pressure increases. As the pressure increases, the volume decreases, and the pressure keep on increases. When the pressure reaches to the P external, the volume become V final. So this is how we can plot the graph for this particular P versus P. Now you can see the green shaded region. This green shaded region represents the work done. The shaded region under the graph represents the work done. So this green shaded region represents the work done, my dear students. Let us study about the work done in detail. When pressure is suddenly when pressure is suddenly increased, my dear students, from P to P external, you can see here that we have suddenly increased the pressure. The initial pressure was P, the final pressure become P external. So the pressure has been increased from P to P external. We can easily understand that change in the volume takes place. So generally the change in the volume takes place at constant pressure. P external is the constant. Suppose the same increase in pressure is done in 5 different steps. Now suppose the same change we are going to do in 5 small changes. So suddenly we do not increase pressure. Suppose the pressure was P initially, then we make it as a P1, then we make it as a P2, then we make it as a P3, then we make it as a P4, and finally it becomes PEX. So suddenly if we do not apply the pressure, but we do it in this manner, then you can see the graph become this way. Now suppose the same work is done in some other way. Let us see what kind of the way by which we do the work. What if we do the same change in a many steps? You can see each line represent the step, and on each step we represent the change. So we are doing the same change in pressure in a many different steps. Now if I want to express this small change into this, so I will have this small changes each time. Now I want to increase, or I want to even make it bigger here. You can see, my dear students, the initial graph when we have done the work directly, it was like this. But now when we are doing it in a small changes, the graph we get is a little different. The different graph that we get is in this manner. See, we do a small changes. So you can see that this green area that we get, see, if the work is done in this manner, we have this area. But if the work is done in the small changes, we get this area extra. This green shaded region is found extra when we do the work in a very small changes. So if the work is done in a very small changes, the area or the graph what we get has been changed and we get it in a different manner. Let us read the text and understand it. If what if we do the same change in many steps? So now we do the same change in many steps, my dear students, and understand it. Let's see. As I increase the number of steps, the slope of graph for each step goes flat and flat. Instead of going this way, it goes now this way. So this region I get an extra portion. If I do the same change in infinite step, where I cannot count the step but they are very small, where for each step slope AP, PQ and AP, PQ, QR and RS are divided in such a small step that the curve almost become linear for each step. So here I am talking about this. See, this is what I'm talking about. That if we think of this AP, PQ, QR, AP, PQ, QR, RS. Now, if you really look at these small changes, instead of the graph going, see here to here, you can see that it becomes flattened. So instead of the graph, overall, if you look at this, the graph is this. But this extra edge, this extra part that we get here, you can easily understand, my dear students, that here we get some extra portion. This is the extra portion that we get. the graph which was in this manner, now it turns to be this manner. So this portion that we get extra when we do the changes into the small changes. So this graph, this PQQRRS, this is what, this which was slopy, it turns out to be flattened. Because we are doing the changes in a very small manner and we are doing it in a very small step. These steps are infinite step and they are very small step. So the slope AP, PQ, QR and RS are divided in such a small step that the curve almost become linear for each step. In such a situation, if we look at the red encircled region of the graph, it looks like this, where each step the graph has been flattened. You can see here, once again, this graph has flattened. So we do changes in smaller steps. The green shaded area, which is extra area that is added under the curve, which shows more work done. So here you can see that if the graph is not flattened, the curve we should get in this manner, but these areas which you can see here, these areas are the extra areas, these green areas which we get when the work is done in infinite small step. When the work is done in infinite small steps, so we get some extra area, and we know that the area under the pressure volume graph, the area under the pressure volume graph is representing the work done. So if the work is done in single step or the work is done in small infinite step, we get this area little bigger than what we can see here. So here, my dear students, when we do it in infinite small step, the area under the curve become bigger. The area under the curve is more. That means more work is done. It shows that more work is done when we do the work in a very small single step. For countable and small changes, we sum up the work mathematically using the sign of summation. So we can write that the work done W is equal to minus P delta V, minus summation P delta V. But if the work is done in infinite simile, small step, instead of summation, we use the new mathematical operation called integration. So my dear students, here you have the new way of doing the work, way of representing the work. Here we use the new mathematical operation which is known as the integration. Integration is represented by this manner. And here you can easily understand that the volume was Vi, which is changed to Vf. We applied the P external force and a small change in volume is represented by dV. So work done W, it is just kind of summation, my dear students, but it is a different kind of summation, and that is why, and that is what it is used for the very small change like dV. So when the volume changes from V initial to V final, we integrate all the changes that is done by very small infinite steps, and each step P external multiplied by dV. So for each infinite simile small step and for all step, if temperature is maintained same, we can say that the work done is isothermal. So now during all these steps, my dear students, if we keep the temperature same, if we do not allow the temperature to be changed, we can say that the work done is done isothermally. Now, my dear students, we want to study about the reversible processes. So a process or change is said to be reversible if process taken place in infinite simile small step. Each step is infinitely small. At any instance, the step can be reversed and the process takes place in a series of equilibrium state such that the system and the surrounding are always in a near equilibrium with each other. Now it's a long definition to understand. So let us divide this definition or the into the small parts. A process or a change. It's said to be reversible because we are defining the reversible process. What happens in the reversible process? First thing is, or the first point is, process takes place in infinitesimally small steps. So the steps are very small and they are infinite. Second, each step is infinitely small. Each step is very small. Third, at any instant, the step can be reversed and the process takes place in a series of the equilibrium state. So at any step, we can reverse the process, and there at each step there is an equilibrium established between the system and the surrounding. So the process takes place in the series, and such many equilibrium state takes place such that the surrounding and is always near equilibrium with the system. So system and surrounding are in equilibrium. Once again, reversible process is a process where the process takes place in very small step. These steps are infinite in number. At any instance we can reverse the step, and at any step if we want to reverse the step, there is an equilibrium established between the system and the surrounding, and when all four these conditions are being followed, such process of changing the state of the system is considered as a reversible process. प्यारे बच्चों, क्या आपको ये चीज समझ में आ गई है?
Yes, sir.
हाँ, अगर कुछ नहीं समझ में आया है तो प्लीज पूछ लीजिए विदाउट फेल, ठीक है? लेट्स मूव फॉरवर्ड. इफ रिवर्सिबल प्रोसेस कैन बी डन एट कांस्टेंट प्रेशर, वी कैन से इट इज isothermal reversible process. See, instead of pressure, please make sense that it is temperature. So if the reversible process is done, because isothermal means temperature constant. So if the process is done at constant temperature, we can say it is isothermal reversible process. From all the above discussion using the graph, we can say clearly that work done in isothermal reversible change is maximum. Please remember, my dear students, that the work done in isothermal reversible change is maximum, because when we do the process in a small step, we get this extra area, and that is why the work done into the isothermal reversible process is maximum. Process other than reversible process are known as irreversible process. Suppose you are asked what is the definition of irreversible process, you can easily answer that the process done uh, other than the reversible process, process other than the reversible process are known as irreversible process. Now, my dear students, we have the next question. Uh, Explain the meaning of W is equal to integration minus integration Vi to Vf, where P external into dV. So here P external at each stage is equal to P internal plus dP. dP is a small change in case of the compression. So P external is equal to P internal plus dP when there is compression, my dear students. Now we are trying to understand the meaning, my dear students. So when it comes to the meaning, work done W is equal to minus integration Vi to Vf, P external into dV. Px, what is the meaning of Px? Px is equal to P internal plus dP when there is compression. What in case of the, but in case of the expansion, my dear students, P external is equal to P internal minus dP. So here we have two cases, either we can compress or we can expand. Expand means volume increases, but in the process, if at equilibrium at any instant, but when there is an equilibrium, we can have the facility to have compression and expansion at the same time, because we can reverse the reaction at any instance. So but in case of process, if at equilibrium at any instant can be released, and each step is infinite small, simally small. change in volume is very small, which is dV, and P external can be written as P internal plus or minus dV. So at equilibrium, my dear students, we for expansion we write P in internal plus dV. For compression we write P internal plus dV. For expansion we write P internal minus dV. But at equilibrium we can write P internal plus or minus dV. And thus, my dear students, the meaning of work done is equal to integration, the volume goes from V initial to V final, V external into dV. So this is how, my dear students, we understand about the change into the volume and how the work is done, or what is the meaning of uh, the work done, V internal minus V external. So, my dear students, today we have studied, or we have revised the first law of thermodynamics, which says that energy can neither be created nor be destroyed in a chemical reaction. In such a condition, my dear students, we can understand that the internal energy is the change into, or change in internal energy is equal to the work done W multiplied by the heat absorbed or the heat released, and this is how we can write that delta U is equal to Q plus W. We have studied the sign convention for the heat and work. Then, my dear students, using the this figure, we have studied about the uh, compression work or the mechanical work. So we have taken a cylinder, we applied some pressure, and due to that the pressure has been changed and the volume is changed by delta V. We have seen that if we plot a graph of P versus V for this, we can get the graph in this manner, and the shaded region represent the work. Now if we do the work in a very small step, the graph which is slopy here, you can see that if we do the work in 5 steps, the graph is still slopy. But if we do it in a very small step, so you can see this region that where the graph becomes almost state, or the curve has been decreased. Now again, if I increase it to certain level, and if we look at into it, so here we are looking into the same region by looking it into more deeper. You can see that when we enlarge that portion, we can see that there is a clear straight line, and this green region that we get is generally the extra work that we get when we do the work in isothermal reversible way. My dear students, isothermal means the temperature remains constant, and this is how we can say that the work done in isothermal reversible process is maximum. To represent the work done in isothermal reversible process, we use the new mathematical symbol. That is what it means. The W is equal to integration P external into dV. That is P multiplied by V. Or so here we can easily understand that V initial, the volume goes from V initial to V final, and overall the P work done is equal to integration P external multiplied by the volume change. Now, when we do the reversible change, my dear students, there are four conditions that has to be maintained. That for a reversible process, the process taken place must be infinitesimally small. At each step, the steps are very small. These steps, we can reverse the step very easily, and the steps take pen into the infinite steps, where each step is reversible. So there is an equilibrium between the system and surrounding at any instant for the step. And this is how, my dear students, when these four conditions are followed, we understand about the reversible process. So for for a compression, we can write P internal plus P dP. For expansion, we write P internal minus dP. But for equilibrium, we should write P external is equal to P internal plus or minus dV. And this is how we understand the meaning of W is equal to minus in integration Vi minus Vf into P external dV. In the next period, my dear students, we will study to calculate and by using this idea of the P internal plus dP, and for we will calculate the exact formula to calculate the work done into the isothermal reversible process, and this is what we are going to get the formula in the next period. We will derive this formula into the next period. I hope you have understood everything, but still if you have any question you can ask me, or you can move to the next class. You are free to ask me any question if you have. बच्चों अगर आपको कुछ पूछना है तो आप लोग पूछ सकते हैं या अगली क्लास के लिए जा सकते हैं. थैंक यू वेरी मच. विश यू हैप्पी लर्निंग. कुछ पूछना है बच्चों? डियर स्टूडेंट्स, डू यू हैव एनीथिंग टू आस्क?
No, sir.
Okay, then you may go to the next class.